No, we are going to do problem 13 from the review packet for the final exam. So we have a 8-kilogram crate is pulled up 5 meters on a 30-degree incline by a rope. So let's put down some of the things we know. We know the mass. We know that the change in position along the incline is 5 meters. We know the incline angle is 30 degrees, and then it says the tension in the rope is 120 newtons. And the crate's coefficient of kinetic friction along the incline, mu k, is 0.25. Okay, so we're going to draw a picture of what this looks like. Oops, that's not a very straight incline. Okay, so that's 30 degrees. And then we have a crate, otherwise known as a square, getting pulled up by a rope. Okay. And then, so we need to write our unknowns, draw a picture, and establish our coordinate system. Okay, so we did draw a picture. We can establish our coordinate system. We'll say that this is x, and that is y. Okay, and what are our unknowns? So I think we're going to have to try and find, so this is what we're given, or what's known, and then unknown is acceleration. And then also it's going to ask us to find V final in part D. Okay, so part B is to draw a free body diagram. And motion map. Okay, so my free body diagram, if I just represent my crate as one little point, I have force of gravity going down. And if you're drawing it not on the picture, you probably want to put in, dotted line to show the surface of the incline, because that makes it easier to draw the normal. Okay, so the normal is going to be perpendicular to that surface, maybe something like that. We have the tension pulling it up, and then we have some amount of friction pulling it back. Okay, and that is my x direction again, and this is my y direction. Alright, so my motion map is going to, again, I'm going to just draw the incline there. So my motion map is going to show an object that's accelerating up the incline, right? So my dots should be getting further and further apart. So acceleration is in that direction. Okay, so part C says apply Newton's second law to find the acceleration of the block. Now the fun starts. Okay, so we are going to, remember the forces are vectors, right? So we're going to sum the forces in the x direction to get max, and then we will also sum the forces in the y direction to get may. Let's just look quickly at the components of gravity in case this is still something that's troubling you. So I'm just going to sketch out the rest of the triangle. That's a similar triangle to the incline, right? So in here is theta. So it means this angle in here is 90 minus theta. So if I look at the components of gravity, let's do it in a different color so you can see it better. So I'm going to have some gravity coming down the incline because it's going to overlap with friction quite a bit. And then the y component of gravity perpendicular to the plane. Okay, so inside my gravity triangle, this is theta, right? Because this is the 90-degree angle. This is 90 minus theta. That makes that theta. So my y component, I'm going to put over here just as a note that FGY is going to be FG cos theta, and FGX equals FG sine theta. Okay, so when I sum my forces in the y direction, I look at my free body diagram and I think about the forces that are acting in this direction. So I have the normal in the positive direction, and then I have this negative component of gravity, thinking about it kind of coming down here. in the negative direction. So I have the normal minus FGY, and my block is not going to jump up off the plane, right? So it's sliding along the plane, but it's not going to accelerate in that direction, so this is 0. So my normal equals FGY, which is FG cos theta, and of course FG is just mass times gravity, so that's mg cos theta. Okay, so the goal really of the y equation is to get an expression for what the normal is. Okay, so then we go back over to the x equation. Again, we look at what is acting in the plus x direction, that's tension. In the negative x direction, I have friction and the x component of gravity, so I'm going to have minus FGX and minus the force of friction equals MAX. And this is what we're trying to find. Right, that's our, yeah, I didn't put it in there, oh my goodness, find acceleration in the x direction. Okay, so, alright, so we want to solve for this, and so we can swap this out, right? So we have tension, which we know, we have minus the x component of gravity, which I'm just going to skip a step there, mg sine theta. We have the force of friction is mu times the normal, and that equals MAX. Okay, so our normal from over here we know is mg cos theta. So we're going to plug that in for that expression. So we get T minus mg sine theta minus mu times mg cos theta equals MAX. Again, this is what we want to find, so we divide everything through by m, and we get that our acceleration is T minus mg. I'm just going to factor that out to get a sine theta plus mu cos theta divided by m. Okay, so we can plug in. So my tension is 120 newtons. My mass is 8 kilograms. G is 9.8 meters per second squared. And then I'm going to multiply by sine of 30, which is a half, plus the coefficient of friction is 0.25 times cosine of 30. Oh, what is that? Radical 3 over 2 or something. Okay, and then divide by the mass is 8 kilograms. And I should get that the acceleration is 7.98 meters per second squared, which we could just round to 8. Okay, and then, so the last part, I'm sorry if I went off the screen there, so the last part, D, is find the final velocity. And then this is great because it's going to pull us back to kinematics. So if I just scooch back up to my picture here, right, we know that the block is going to travel up the incline 5 meters. Okay, so now we know our acceleration, we know the distance traveled. We know also that it starts at rest, which I forgot to. I don't want to make you guys dizzy, but I'll put it back up here. We do know that V initial equals 0. Okay, so we're just going to do a kinematic equation of describes the motion along the incline. So V final x squared equals V initial x squared plus 2ax delta x. And of course, there's always multiple ways to do this, right? You could actually solve for the time using the position versus time equation, and then plug in and get the velocity at that time. When just using this, if I know the distance and I know the acceleration and I know my initial velocity, this is the quickest way, right? Because my only unknown is just a one step to get to the final velocity. All right, so we said V initial is 0. So we end up solving for V final x is just the square root of 2ax delta x. So I can plug in my values. 2 times my acceleration squared times delta x, 5 meters. And what do we get? The final velocity is, you guys can calculate, meters per second. Ta-da!